Right, so we're now moving on to chapter 9, uh, which is all about certain mathematical objects called relations, which share a lot of similarities with what you would sort of colloquially call a relation. Uh, and so I think, right, so especially in the last part of chapter 8, a lot of what we were doing was pretty technically demanding, and I think this chapter will at least be a bit of a break, and I think this chapter will be a little bit easier than the last chapter, especially the material involving the general inclusion exclusion formula, which is pretty complicated. Uh, right, and as I mentioned before, the last lecture was ended up maybe being a little bit too long, so this lecture is going to be a little bit shorter, and then sort of just give a broad overview of what mathematical relations are, and then in the subsequent lecture we'll go into a little bit more detail about certain very important types of relations called equivalence relations. And so just looking forward, this class is moving towards like the final unit, which sort of broadly speaking is focused on graph theory. And so in order to talk about graph theory, we need to sort of begin by talking about relations first. Relations are also more broadly in mathematics very important concepts, and they show up all over the place, and we'll see some examples of that as well. Uh, right, so what is a relation mathematically? Well, at least informally, a relation as we know it from day to day is basically a property that connects, or I know this is a little bit redundant, connects or relates one object to another, right? You have two different objects, and the relation is some property that makes those two objects connected to one another in some way. And of course, this is very abstract because it's going to show up in a lot of different ways. Uh, Right, but in order to make this work in math, we have to have very precise definitions. So what is the mathematical definition of a relation? Well, let's suppose we have two sets A and B. Uh, so a binary relation from one set A to the other set B is formally a subset of the Cartesian product of A and B, meaning it's some particular collection of ordered pairs, a, little b, where little a is in the set big A and little b is in the set big B. And so you want to think of this in the following way, right? So if I have an ordered pair a comma b in my relation, that means I'm relating a to b, right? I'm saying a is related to b. And the way to model this mathematically is to, again, use these ordered pairs. Uh, and so we'll very frequently denote a relation by capital R. R is just for relation. And so remember from the definition up here, R is going to be viewed as a subset of the Cartesian product of A and B. Right, so R is some particular choice of some collection of ordered pairs where the first element in the ordered pair is from A and the second element in the ordered pair is from B. And then the ordered pairs that are chosen are all different pairs of elements which are related to one another by R. Uh, right. And so in terms of shorthand notation, right, if you're writing a lot of Cartesian products and ordered pairs all over the place, sometimes the notation gets kind of messy. So we may often write just A, R, B to mean that this ordered pair A comma B is in the relation R. And how would we say this verbally? We would just say, well, A is related to B by whatever relation we happen to be working with. Uh, right, and so this is kind of abstract, but let's look at some examples, and hopefully it will become a little bit clearer. So in the first example, my set A is going to consist of all cities in the world, right? So all cities throughout the globe, and I'll let B denote the set of all countries that are in the world. And so we'll define a relation from A to B as follows. So given a city A, which is in the set capital A, and a country B, which is in the set capital B, we'll say that A is related to B if the city A is in the country B, right? And so in particular, if we go back to the last definition, the sort of technically speaking, the relation R is going to be the set of all ordered pairs, where in the first entry I have some city, and in the second century I have some country, but I'm not looking at all such ordered pairs. I'm only looking at ordered pairs where city A belongs to country B, right? And this is my relation. A city is related to a country if the city belongs to that country. So for example, if I look at the ordered pair New York, USA, then this is in my relation because New York City is in the United States. And also if I look at the ordered pair Rome, Italy, then this is also in the relation R because Rome is in Italy. Uh, However, if I consider the ordered pair, for example, Tokyo, comma, France, well, this is an element of the Cartesian product of A and B, right? Because the first entry is a city, and the second entry is a country, but Tokyo does not belong, is not in France, right? So by definition, this ordered pair is not in the relation, right? So these first two ordered pairs are in the relation, and the second one is not. And sort of maybe less formally, given this relation R, New York is related to USA, Rome is related to Italy, but Tokyo is not related to France. Right. And of course, when I say something is or is not related to something else, I mean, it depends on the definition of the relation. So you always want to keep in mind, what is the definition of the relation you're working with? Right, and so the next example will be maybe more mathematical. So I'm going to let A be the set of integers between 1 and 10, including 1 and 10, and I'll also take my set B to just be A again. And so I'm going to define a relation now on this set A from A to B. Well, in this case, B is just equal to A. But I'll define the relation R by saying that an integer A is related to an integer B, or ARB, if A divides B, right? And so what does this mean? This means that if I look at A divided by B, then I get another integer. Right, of course, if I look at this fraction, this is always going to be some rational number, but I say that A divides B if it happens to be an integer. Right, so we can just sort of list out some examples of ordered pairs that are in our relation. For example, 1 divides 4 because 4 over 1 is 4. 3 divides 9 because 9 over 3 is 3. And 5 divides 10 because 10 over 5 is 2. Right, so the fractions in this order are all integers. Right, so these are all in the relation. However, if I look at these two ordered pairs, say 5, 3, and 4, 2, these are not in the relation, right? Because if I look at 5 divided by 3, well, that's a fraction. That's not a whole number, right? Because 3 does not divide evenly into 5. And right, sorry, I just noticed there's a typo here. So this should say, right, so A divides B. This should be reversed. It should be B divided by A. I'm sorry about that. Right, so for the first 3 ordered pairs, 1 divides 4, 3 divides 9, and 5 divides 10. The next 2 ordered pairs, 5 does not divide 3 because, right, 3 over 5 is a fraction. And also 4 does not divide 2 because 2 over 4 is equal to 1/2, which is not a whole number, right? Right, so you should imagine this is B over A, not A over B. I'm sorry about that. Right. And so notice that order definitely matters, right? So the relations are in general are not going to be symmetric, meaning if A is related to B, it doesn't mean that B is related to A, right? Because for example, if we look at the last example, well, 2 comma 4 is in the relation because 2 divides 4, right? 4 divided by 2 is 2, which is an integer. But if I switch the order, then 4 does not divide 2, right? Because 2 divided by 4 is a fraction, right? So this is not in the relation. 4, 2 is not in the relation, even if 2, 4 is in the relation. Right. So you have to be very, very careful. Like it's very tempting to think, well, if some quantity A is related to some quantity B, then also B is related to A. And sort of in like natural common language, we usually use the word relation in this way, but mathematically it's not necessarily the case. So relations for which this is the case are called symmetric relations, which we'll talk about more later. This is an example, the second example, which is not symmetric, meaning if you flip the order, they may no longer be related. Right. And something that's worth pointing out is that if, for example, if I have a relation from a set A to a set B, and A and B are distinct sets, well, remember, R is a subset of the Cartesian product, right? And so if I flip the order, well, this may not even be defined, right? Because B belongs to the larger set B, but B may not belong to A, so it may not even make sense to define this object here, BRA, in the sense on the previous slide. Right, and so one thing that's worth pointing out is we've already encountered a very broad class of relations in sort of a pretty abstract level, because you can view, let's say I have a set A and a set B and a function from A to B. I can always view a function as a relation, and in particular, I can interpret the function f as a subset of the Cartesian product of A and B, which is exactly what we defined a relation to be. How can I do this? Well, right, so notice if I have an element little a in A, my function f sends little a to a unique element of B. And so, well, let me just consider the ordered pair where I have little a and then the element that the function sends it to. And this is a way that the function gives a relation between the two sets. So more precisely, I can view my function as the set of ordered pairs in the Cartesian product such that B is equal to f of A, right? So the second entry here is the function applied to the first. And so more succinctly, you can write it like this. And so if you go back a few slides to the definition of what a relation was mathematically, this is a particular example of a relation, right? So all functions are examples of relations in this abstract way. Right, and how is A related to B? A is related to B if the function f sends A to B, right? That's basically what this all means. And so maybe a quick example, let's for example, suppose that A and B are both equal to the unit interval between 0 and 1, including the endpoints, and let my function f be f of x is equal to x squared. And so what is the relation here? Well, the relation is A is related to B if and only if the function sends A to B or B is equal to A squared, right? So A will be related to B if B equals A squared. And remember, the order here matters, as I'll mention again in a second, right? And so in particular, even though these two sets are the same, this is not symmetric, meaning even though if A is related to B, it doesn't necessarily imply that B is related to A. For example, if I consider the ordered pair 0.5, comma 0.25, well, 0.25 is 0.5 squared, right? So this tuple or this pair is in my relation. But if I switch the order, well, 0.25 comma 0.5 is not in my relation, because if I look at here, A is 0.25. If I look at 0.25 squared, that's not going to give me B, right? So even though this first tuple is in the relation, this is an example where if I switch the order, it's no longer in the relation. So we would say this is not symmetric. Right. Okay, and so right, so this is sort of more generally speaking how to define a relation from one set to another. A lot of the important examples we're going to be looking at is going to be in the situation when B is equal to A. We've already seen a few examples of this, right? So instead of having a relation from A to some other abstract set B, we'll just have a relation where we'll just be looking at relations where A and B are the same set. Right, so if I go back to the definition from before, a relation will just be some subset of A cross A, or some collection of tuples containing elements from A. And in this case, we just simply say that R is a relation on A, right? It's sort of redundant to use A twice, so we just say R is a relation on A. So maybe one simple example, let's suppose A is just the set containing 1, 2, 3, and 4. And let's suppose I just sort of construct a relation sort of arbitrarily. So let's say my relation is this collection of 5 ordered pairs, right? So 1 is related to 1, 1 is related to 2, 2 is related to 3, and so on, right? I just sort of pick them arbitrarily. Right, and so this is an example of a relation on A. And so there are some sort of useful visual tools for understanding a given relation. And so in particular, we can visualize relations like this using graphs or directed graphs, right? So when we move on to chapter 10, everything we're going to be talking about are all graphs. So I'll go into more detail about this then, but basically a graph, sort of a combinatorial graph, is some collection of finite points which are called vertices, and then you have edges or arrows that are connecting the vertices. and it's going to be a directed graph in the case where you have arrows, right? And the arrow sort of indicates, well, this has a one-way relationship with, right? For example, here the one has a one-way relationship with this other point one, and maybe it doesn't go backwards. Right, and so what I've done here is I've taken this sort of arbitrary relation R, and I've sort of represented it in two different ways using graphs. And so the first image over here is basically using the interpretation of this relation as a function, right? We've seen lots of examples of functions where I've defined like with arrows. And so here, each arrow, I have an arrow if and only if this point is related to the endpoint of the arrow, right? So I have 1 is related to 1, so 1 goes to 1. I have 1 is related to 2, so 1 goes to 2. 2 is related to 3, so 2 goes to 3. 3 is related to 2, so 3 goes to 2. And finally, 4 is related to 3. Right, so this is, technically speaking, this is an example of a graph, although this is also just, you can think of this as just using the function picture that we've had before for lots of examples of discrete functions. And so this image over here is a different way of representing the relation, and this is a legitimate example of something called a directed graph. And so I have here 4 different vertice points or vertices, which represent the 4 elements of my set A. And I have an arrow from one vertex to another if and only if the starting point of the arrow is related to the end point of the arrow, right? For example, 2 is related to 3, so I have an arrow starting at 2 and ending at 3. And also 3 is related to 2, so I have an arrow starting at 3 and ending at 2. Well, what's this circle over here? Well, notice 1 is related to itself. And so in order to draw an arrow from 1 to itself, people usually use loops, right? So in graph theory terminology, these are called loops. And so I have a loop starting at 1 and ending at 1. Right? And so this is an example of what's called a directed graph, which we'll analyze more precisely when we move on to chapter 10. But the main point here is that these are nice tools for visualizing relations, and also sort of the slightly more advanced way of talking about this is that relations really just, there's sort of like a correspondence between finite relations and directed graphs, and they're really mathematically the same thing in some sense. For now, just think of them as nice ways to visualize relations. Okay. And so this is a way to visualize relations using a graph. You can also visualize or sort of compactly write relations out using a matrix. And so, for example, let's suppose I'm working with the same set A, which is the set 1, 2, 3, 4, and the same relation on A from the last slide. Well, we can represent this this relation via a square matrix that contains only zeros and ones. And so in particular, right, so remember the matrix will have some row of numbers, some rows and some columns. And well, in row I and column J, we'll put a 1 if and only if the pair ij is in the relation. And in all other spots which do not correspond to things that are in the relation, we'll just put zeros. So for example, for this relation here, this is the matrix that we get, right? So this matrix has, remember, rows are horizontal. So this is row 1, this is row 2, this is row 3, and so on. And columns are vertical, so, right? So this is column 1, and then this is column 2, and so on. And so, right, so let's just go through this relation. So I have 1, 1 is in my relation. So that means if I go to row 1 and column 1, which is this point here that my mouse is hovering over, this should have a 1, which it does. And if I move on to row 1 and column 2, row 1 and column 2 is this entry right here. This has a 1 because it's in the relation. However, if I move here, this is row 1 and column 3. Notice that 1, 3 is not in the relation, so I'm putting a 0 here, right? And similarly, 1, 4 is not in the relation, so there's a 0 here. Right? And then what I've done, like throughout the rest of the matrix, you can maybe pause the slide for a second and check that I put a 1 in exactly the corresponding positions from this relation. For example, well, 3, 2 is in my relation, so I should have a 1 in row 3 and column 2, right? So if I go down to row 3 and column 2, right, I have a 1 there. And so again, this is a sort of a nice compact way to represent a relation, as long as, or to store a relation, as long as it's not too big, right? You can store it as, you can view it as a matrix like this of ones and zeros. All right, and so the final thing I want to talk about for today's lecture is to just quickly go over three very important types of relations, and then in the next lecture we'll go into more detail and talk about why these are important types of relations. Uh, excuse me. Right. So the first important type of relation is something called a reflexive relation, and so this sort of seems maybe a sort of redundant or a trivial definition, but we'll see examples where right, that indicate you need to define this. Basically, because mathematically relations can be very abstract and lots of weird things can happen. Uh, so a relation, let's say we have a relation R on a set A. So it's said to be reflexive if the ordered pair that contains A twice is in R for any element of the set, meaning every element of the set is related to itself. Uh, right, so for example, if we consider the set A 1, 2, 3, 4, let me call this relation R1, which I just listed out here. Well, this relation is reflexive. How do we know it's reflexive? Well, I need to check that for every element of A, the ordered pair AA is in this relation. So that means I need the ordered pair 1, 1, which is here, and 2, 2, which is here, and 3, 3, and then 4, 4. Right, so since this contains all such ordered pairs, by definition, it's reflexive. However, if I consider this other relation, which I'll call R2, this is not reflexive. In particular, the ordered pair 3, 3 and 4, 4 are not in this relation. So if we're talking about the relation R2, then 3 is not related to itself and 4 is not related to itself, and therefore this is not reflexive. Okay, and so another class of important relations, which we talked about a little bit earlier, are relations which are called symmetric. And so formally, if I have a relation on a set A, it's called symmetric if B comma A is in the relation whenever A comma B is in the relation. And so what does this mean? This means that if A is related to B, then this has to imply that B is related to A, right? So it means I can switch the order and stay inside the, whenever I switch the order, I get something that's also in the relation, right? If I switch the order of the ordered pairs. Right, and so one way to think about this is, right, A is related to B if and only if B is related to A, right? You need symmetry, you need both. We've seen plenty of examples already which are not symmetric, but let me just do one example which is symmetric. Right, so in this case, I'll let my set A denote the set of all residents of the state Illinois, and I'll define my relation R on the set by saying A is related to B if and only if persons A and B live in the same city. Right. Right. Well, what happens if A is related to B? By definition, that means person A and B live in the same city. But if person A and B live in the same city, then it doesn't matter what order I say that in, right? Person B and A live in the same city. It's kind of a tautology, right? So if A is related to B, meaning these two people live in the same city, then of course B is related to A, right? Because they still live in the same city if I switch the order that I say this in. And therefore, this is a symmetric relation. Right? And also, it's also reflexive, right? Because person A lives in the same city as themselves, right? Right, and so again, as I mentioned a second ago, if you want examples of relations which are not symmetric, there are plenty of examples earlier in the slides. Right, so there's another notion, another type of relation which has to do with symmetry, which is a little bit more complicated than just not being symmetric. And so these are called anti-symmetric relations. And so again, I want to caution, anti-symmetric does not mean that it's not symmetric. Like there are examples of relations which are neither symmetric nor anti-symmetric. So what is an anti-symmetric relation? Well, a relation on a set A is said to be anti-symmetric uh, if it has sort of the least amount of symmetry possible, meaning that if I know that the ordered pairs A, B, and BA, sort of the symmetric ordered pairs, both belong to the relation, then this can only happen if A is equal to B. Right? And so this means there are no symmetric terms in the relation except possibly ordered pairs where each element is the same. And so there's like the least amount of symmetry possible. So for example, again, let me work with the set A, which is 1, 2, 3, 4. This is an example of a relation which is anti-symmetric, right? Meaning it contains 1, 1, but there, like for the other three terms, if I flip the order in each of these three terms, I get something that's not in the relation, right? So this is anti-symmetric. And you can also check, again, maybe if you pause the lecture for a second, that this relation is not reflexive and also not symmetric. But again, I want to caution that just because it's not symmetric, that doesn't necessarily imply it's anti-symmetric, right? For example, if I added 2, 1 to this relation, it would still not be symmetric, but it would also not be anti-symmetric, right? All right, and so there's one final type of relation I want to talk about, which is important, and then we'll be done for the day. And so these are called transitive relations. And so what is a transitive relation? So again, we'll have a relation R on a set A. And so this relation is said to be transitive if, well, let's suppose A comma B is in my relation and B comma C is also in the relation. If both of those two facts together imply that A comma C is in the relation, then it's said to be transitive, right? And so the idea is, well, A is related to B, B is related to C, so A should be related to C, which is what this says. This is not true for sort of abstract mathematical relations, but those for which it is true are called transitive, right? And so this means that A related to B and B related to C together imply that A is also related to C. And so finally, let me just do one final example of a transitive relation. So in this case, well, there's another typo here. A should be 1, 2, 3, 4, not just 1, 2, 3. Let me call my relation R1 to be the relation I've listed out here. Well, you can check that this is transitive. For example, here I have the ordered pair 1, 2, and here I have the ordered pair 2, 3. And therefore, 1 is related to 2 and 2 is related to 3. And so in order for this to be transitive, I need to have 1 related to 3. So 1, 3 should be in the relation, and it is, and you can check right here. And similarly, well, notice that 1 is related to 3, and 3 is related to 4. And therefore, in order for this to be transitive, I need to have 1 related to 4. But you can see 1, 4 is right here, so it is transitive. However, if I consider this other relation R2 that I have here, this is not transitive, in particular because I deleted 1, 4, right? So this has 1, 3 and 3, 4. So 1 is related to 3 and 3 is related to 4. But for this second relation, 1 is not related to 4 because the ordered pair 1, 4 is not an element of this relation. And so therefore R2 is not transitive. And finally, just finishing up, if you go back to this other example where A is the set of all residents of Illinois, and I define a relation by saying person A is related to person B if they live in the same city, then that's also transitive, right? Because if person A lives in the same city as person B, and person B lives in the same city as person C, then of course A and B have to live in the same city as well. And so if A is related to B and B is related to C, then A is related to C. Right, and more succinctly, you can use ordered pairs to write that out. And so this second example involving residents of cities is sort of more like sort of in common language what we think about when we say something is related to something else. Like in common language, relations are usually transitive, but you have to be very careful because mathematically they're more general. And so, right, so here's an example of a relation which is not transitive right, on this set A. Right. And so the reason these three types of relations are very important is because they're used to define certain important relations, which are called equivalence relations, which are sort of prevalent throughout all of mathematics and computer science and things like that. And so the next lecture will be all about equivalence relations. Right, but we're done for now.